Alright, let's go ahead and open up to page 19. We're going to start our next section today. Euler's method. Maybe you've heard of him before, maybe you haven't. But we're going to see who this lovely lovely person is on your paper. So, Euler's method, I think is kind of interesting how he developed this, but it's a way of us, or it's a way for us to determine a solution curve to a differential or derivative problem that might be very difficult to solve by hand. So I have this little kind of paragraph at the beginning. I'm just going to go through it kind of quickly. I know you guys can read it. But just as a refresher, because we did a lot with derivatives last year, a differential equation normally looks like dy over dx, or y prime, equals something. Okay, we know that. That cannot be solved. Okay, we're specifically looking at those cases. Sometimes they can. Okay, we did a lot of those last year. But Euler's method is a process for us to figure out solutions to more difficult differential equations. Last year we talked about a slope field. You remember that? Okay, so if we were, I'm just going to try to draw one real quick. You don't have to worry about drawing one. Okay, so maybe we had a slope field like that, and they would ask you to plot a point and draw the solution curve. Remember how you would like trace the slopes to the left and the right? Remember doing that? Okay, so a slope field is a way for us to get a visual representation about an equation that fits those derivatives, okay, those slopes. But what Euler focused on is figuring out, well, what is the equation of that graph? Okay, and we solved those last year. Do you remember, like, separating the variables, integrating both sides, doing all that? Okay, we did easy ones. Those are ones you could do by hand. But again, Euler was looking at ones that were more difficult. And actually, there's an entire college class called differential equations that goes into how can you solve those more difficult ones by hand. Like, it's an entire class just for this one subject. So there's a lot more that goes into it. But what Euler's method did, he was looking at trends in solutions, okay, looking at those slopes. We're going to go ahead down to the third paragraph for a second. Euler's method basically involves walking out along a tightrope. Okay, walking out along one of these slope field lines from an initial point along its tangent line. But instead of walking along the tangent line for the entire graph, he jumps from tangent line to tangent line, which is creating a more accurate curvature to your solution curve. Just like when you do a slope field, when you trace it to the right, you move from this slope at the point to this slope on the right. And the more slopes you have, those are the ones that you continue to follow. So instead of just traveling along one tangent line, we're going to travel along multiple ones. Okay, so this little graph at the bottom, we're going to do a visual to help this make sense. But what we're doing is we're trying to figure out approximately where are the solution points located on a particular slope field graph. Okay, for instance, as an example. Okay, so let's go ahead and say, I know this, we're going to say that this is the exact solution curve. Okay, they give it to us, but I want to show you how Euler approximated this solution curve. Okay, he tried to get points really close to this graph, but not quite exactly. So just like in any slope field problem, they give you a starting point, right? They tell you find the slope or find the solution that goes through this point. You'll always have that beginning point, and let's just say, for instance, that's right there. Okay, so we'll label this point we know. We'll also label this point as x sub 0 and y sub 0 to represent that beginning idea. All right, and since we're dealing with differential equations, aka derivative equations, you normally have y prime or dy over dx, whatever notation you want to use. This equals some equation, and that equation typically has x's and y's in it. Maybe sometimes just x's, sometimes just y's, but usually they have both. Okay, so we're going to say that we have a derivative equation that has x's and y's in the expression itself. So what Euler did is, with this starting point, he drew a tangent line. Okay, maybe something like that. And he imagined walking on this tangent line and just stopping at some random point. Maybe we'll say he stopped there. Okay, so he went from his beginning point to this new point. Maybe we'll label this one x1 and y1. Are we doing okay? So notice how Euler's approximation point, that blue one, is fairly close to the actual point, right? So his approximation is pretty accurate. Okay, it's pretty close. But do you realize that if he continued to walk across that tangent line, his approximation points would get worse? They're not very accurate, right? So what he did is, instead of continuing along that tangent line, he created a new tangent line that would eventually be closer to the actual curve. Okay, so if this was his approximation point, he took the slope from the actual graph and he drew a parallel tangent through his approximation point. And now he kind of repeats the process. He walks out along this new tangent line to get his new point. Okay, maybe we'll label that x2, y2. And do you realize how his approximation point is fairly close to the actual one, okay, but not as close as his previous approximation point, right? So there is some error in here because he's just approximating these points. He's not finding them exactly. But do you see how jumping to a new tangent line made him more accurate, right? Instead of keeping along the red tangent line, by jumping to the green one, he became more accurate. And if you wanted to repeat the process, you could draw a tangent line at that exact point, draw a parallel one from the red point, and you can continue the process. Okay, you can get as many points as you want. Is that making sense? Do we see that visual? Okay, so what we're going to do is we're going to label certain things on here to help us make sense of this Euler's method, this technique to find these approximation points. We're going to say the distance between the beginning point and the first point that you find, or even the first point and the second point you find. We're going to give that some distance of h. Okay, sometimes that's referred to as your step or your interval. So hopefully we realize that in order to get from x sub 0 to x sub 1, we would just have to add h, right? Add that distance, okay? Let's talk about, though, how we can go from y sub 0 to y sub 1. So we have some way to figure out how we start with one x value and get to the next, but how do we start with one y value and get to that next one. So what we're going to do is we're going to visualize kind of a little a triangle in here. Hello? Yes. Uh-huh. Sure, no problem. Uh-huh. Bye. You left your lights on in your car. Can you see your car? Yeah.
I mean, I can't see it, like, see it, but I know it's up there.
You know it's right out there? Okay. Do you want to go shut them off? I don't want your battery to die. Okay. Can someone go with her and let her back in through the student entrance? Okay. I did that over the summer and my car died. So I need you to go do that.
Thank you.
Uh-huh. Do you guys want to wait till they get back? Yeah. Okay. We're in this together, right?
Yeah. I'm looking out for them. Okay, we have art and we have Halloween, so. And our shape is triangle and our color is fire, so. We're doing candy corn and then we're gonna have them like color in the candy corn like the orange. But mine is teaching my first one. I'm gonna teach it to 6. I'll let us know. This is probably this one.
All right, so we already know that the distance from the beginning point to our new point is h. Okay, so we can label that. But we're going to try to figure out what's this distance here. Okay, what's the distance between the y's? Yes, sir?
I just heard the back door. Was somebody outside?
Yes, I got a call from Jen saying that her lights were on,
Okay.
and if I could see her to let her go out.
Okay.
Okay.
Just making sure.
That's okay. Thank you.
It's like we let her go out and she starts off.
That's funny. All right, so the distance between the x's is that value of h. Okay, that's step. Let's go ahead and try to figure out what's the distance between the new y coordinates. Okay, and this is all going to come back to the idea of a derivative or a slope. Okay, so if you think about slope and the little triangle we drew, we're technically trying to label the rise and the run. Or I did that backwards. There's the rise, there's the run, right? Okay, and we already know that the slope comes from that tangent line, aka derivative. Okay, and if you look it up here, we have the slope is whatever differential equation that they gave us. So what we could write is that the slope, that differential equation, is equal to the rise over the run. We already know the run, though, is h. That's step. So how can we figure out what the rise is? Can you solve for rise in that equation? You guys want to multiply the h over? Okay, so the rise in our little triangle here would be h times the slope. Now what's a little tricky is that the slope comes from the previous point you used, right? Because we take the previous point and we draw that tangent line, which eventually gets us to the new point. So what we're going to do down here is label x sub 0, y sub 0 to represent the slope from the previous point. So it looks like in order to get our new y coordinate, we have to take the previous y coordinate and add the step times the slope from the previous point, and that would give us the new point, the new y coordinate of the approximation point. It's going to be a very repetitive process because we can keep drawing these tangent lines, we can keep getting these new points, and we can keep adding h to the x coordinate and adding h times the previous slope to the y coordinate to get our points. Okay, that's what we're going to focus on today. Something else I want to focus on is the idea of the shape of the graph in terms of the approximation points that we have. Notice how these approximation points that Euler found are less than the actual ones. Why do you think they're less than? What do you think is causing these tangent lines to be underneath the actual graph? Yeah? Exactly. So something's going on with the shape of this graph that's causing the tangent lines to be below it. I'm hearing it?
Concave.
It's concave up. Okay, so we'll say, my pen's about to die, if the approximations are less than the actuals, then your solution curve is concave up, and vice versa. If the approximation points are greater than the actuals, then your graph would be concave down. I think we saw a little bit of that last year, how the concavity determines whether you have an over or an underestimate. All right, so on the back of that paper, there's like a little box at the top of the page. We're going to fill in what all the different notations and symbols mean for this Euler's method. So we said that x sub 0 represented the known x value that you begin with from the point. The y sub 0 is the known y value from the point you start with. What did h represent? There you go, the difference between your beginning x value and your new x value. So you could write that out. Sometimes you'll see it in a problem labeled as your step. And then we identified this capital F function with the x's and y's in it as your derivative or differential equation. But if it's a derivative equation, that's just representing your slope at the previous point. So with all these different variables and notations, we're going to write two equations to help us figure out the new x-coordinate and the new y-coordinate of every approximation point that we want to find. Okay, so let's go ahead and say x sub n plus 1. Okay, if we want to go one more than the beginning point, or one more from the previous point, you simply add 1, and we'll say y sub n plus 1 as well. So if we wanted to figure out the next x coordinate, okay, we said we had to take the previous x coordinate, which would be one less than the one that you're currently trying to find, so that would be just n, and we're going to add h. Okay, so to find the next x coordinate, you take the previous one plus your step. The y's are a little different though. If you want to figure out your next y coordinate, you had to take the previous y coordinate, but add the step times the slope at the previous point. I want to write plus. Okay, so mathematically speaking, I know it looks weird. There's like letters everywhere. But when we start to get to some numbers, I hope it's going to click. Okay, so x values are simple. We just add the step every time. But the y values, we have to add the step times the slope at the previous point. Okay, so we're going to take a look at our first one with numbers. So hopefully this kind of clicks. Given is the differential equation. Okay, so this is what you use to help you figure out any slope you want. And you know this beginning point. So we can label x sub 0 as 0 and y sub 0 as 5. Okay, in terms of a slope field, that would be the point you'd plot and then follow the slopes if you wanted to draw a graph. Okay, but in this time we're trying to find approximation points that would be on the graph. So we're going to try to approximate y of 0.8 using Euler's method with 2 equal steps. So you want this h value to be the same every single time. Okay, 2 equal steps. So if we think about this 2 equal step idea, notice how the x value we're starting with is 0, and the x value we're trying to approximate is 0.8. So how can you evenly divide up that interval with 2 equal sections? What does your h have to be? Can we figure out the step? If you're going from 0 to 0.8, yeah? 0.4. Okay, so there's our step. Do you see how that we can figure that out? Okay, 2 equal steps. So you have your beginning x value and the ending one that you're trying to approximate. So what I like to do is kind of create a table to make sense of all this. All right, so our beginning x value was 0. Our beginning y value was 5. Let's go ahead and find the new x value. So in order to figure out the new x value, we have to take the previous x value plus the step. So we would take 0 plus the step of 0.4, which would just be 0.4. The x's are always the easiest ones to do. All right, let's go ahead and try to find the new y value. So to figure out the new y value, you have to take the previous y value, which we said was 5, and we have to add the step times the slope from the previous point. So we said the step was 4. How can we figure out the slope from the previous point? Do we know something that represents slope? What do you think, Caitlin?
Use the equation up top.
There we go. Okay, your derivative equation, aka slope equation. So we're going to use this equation, and we have to figure out the slope from the previous point, aka this x sub 0 and y sub 0. Now your derivative equation only has an x in it, so we would only have to plug in the 0 from the previous point in for that x. So we have the previous y value plus the step times the slope from the previous point. coming from that slope equation. So from there, it's just kind of a calculation work for you. If you need to use a calculator, go ahead. We would have 5 minus 0.8. So our new y value is 4.2. We doing okay? All right. We're not quite done yet because we're trying to approximate an x value of 0.8. So we still have to keep going in our table here. If we add another step to the previous x value, that would take us to the 0.8 that we want. So now we got to figure out the next y value. So to figure out the next y value, we need to take the previous y value, which we said was 4.2, okay, not 5 anymore, 4.2, plus the step times the slope from the previous point. So if we're only dealing with x values in our slope equation, we're going to plug in 0.4, because that's the previous x value, into the equation, and from there we can calculate to get our new y value. This would be our approximation. Can you guys check it? Can we get 3.56? Okay, so this is Euler's method. Okay, it's just a repetitive process depending on how many points you need to calculate, how big you want that step to be. Hopefully we realize that the smaller the step value, the more accurate, because you're using a lot more data points than just larger differences between them. Okay, so the smaller the step, the better it is. So Euler's approximation is 3.56, but we know that's not the actual one. Okay, it's going to be fairly close to the actual one, maybe a little higher, maybe a little lower. Okay, so part B here is actually going to tell us to solve this derivative or differential equation by hand. Okay, so this should be an easier one for us to do, something like we did last year. And we have that same initial condition to help us figure out what is the actual value at this 0.8. So to solve a differential, we have to separate those variables, get all the y's on one side, x's on the other. So I think you guys can just multiply over the dx. Let's go ahead and integrate both sides. Okay, don't forget the plus c. Can we figure out what c is? Okay, let's go ahead and use that initial condition. If we were to plug in 0 for all the x's, the y value should be 5. But if we plug in 0 for all the x's, they're just going to go away, which means we're left with the c value of 5. So we have y equals 1/2 x squared minus 2x plus 5. So here's the exact equation of the curve of the graph that goes through the 0, 5 point. Okay, so let's use this equation to now calculate the value if we were to plug in 0.8. So you may need a calculator. If you were to plug in 0.8 for those x's, what would the actual coordinate or y value be? We get 3.72? Yeah? Okay. So if that's the actual point, I know this isn't part of the problem, but just out of curiosity, if the actual point is located at 3.72 and Euler's approximation for it was 3.56, do we know the concavity of the graph at this point of 0, 5? Yeah.
Concave up.
Concave up, there we go. Okay, so since the approximation was less than the actual, the solution curve or graph, whatever you want to say, is concave up at the specific point of 0, 5. Okay? We might not know what the concavity is at other points, but we know for certain at 0, 5 is concave up, because that's the point that we started with. We doing okay? All right, let's go ahead and try another one. Let's see, our slope equation, our differential equation is given to us. And if the y value is 3 when the x value is 2, you use Euler's method with 5 equal steps to approximate the y value when x is 1.5. Okay, so it looks like we're starting with an x value of 2. We want to approximate an x value of 1.5. And we need 5 steps or 5 iterations, 5 processes to get us there. So what might our step be? Might be a little tricky. Yeah. It's negative because we're going backwards. Okay, negative 0.1. Notice how we're starting with 2, but we want to approximate 1.5. Okay, so we're moving to the left, graphically speaking. Okay, so let's go ahead and we'll fill out a table. You don't have to do this. This is just what I do to keep everything organized. Okay, so we're starting with 2. And if we go backwards 0.1 every time, we'll have 1.9, 1.8, 1.7, 1.6, 1.5. Okay, the x's are always the easiest to fill out. So let's now figure out the y's. We're starting with a y value of 3. To figure out the next y value, we have to take the previous y value plus the step, but notice how we'd be adding a negative, so that we'd have to subtract 0.1. And then we have to multiply that 0.1 by the slope from the previous point. So notice how your slope equation has an x and a y in it. So you have to take the x value and the y value from the previous point to plug in there. So we would have 2 times 2 and then minus 3. So it might take some calculation, but you can go ahead and figure out your new y coordinate. I think you get 2.9, right? Okay. So when you're going through Euler's process, you know how on the AP test you can round or truncate to 3 decimal places? Okay. You should really only round or truncate at the very end. So in this process, if you get a number that has like an infinite amount of decimals, okay, try not to cut it off at 3. Maybe go to 4 or 5. That way you're a little bit more accurate. Okay. So let's go ahead now and try to find the next y coordinate. Okay, we got to take the previous y coordinate, which we just found was 2.9, plus the step times the slope from the previous point. So in your slope equation, we're going to plug in 1.9 for x and 2.9 for y. You get 2.81. Okay, you guys starting to see the process to it? Okay, you just keep going and going and going until you reach the end approximation you want. Right, so I'll let you guys go through the rest until someone can tell me what our Y value approximation is for 1.5. Any thoughts? What do we got? Yeah?
2.61, yeah, 1051.
5, 1. Exactly? That's it?
Yeah.
Looks good to me. Can we get that? Yeah? Perfect. Okay. Bell's going to ring in a little bit. We'll do more with this Euler's method tomorrow. We doing okay? Think it's not too bad? Okay, it's just a repetitive process. Okay. Also tomorrow, homework due from the 1.1 section with volume cross sections. Okay, I'll be collecting that tomorrow.